Welcome to Lecture 7 of Differential Equations 1, and today we're going to be covering a few other methods of solving first order differential equations, ordinary differential equations. Okay, so thus far we've covered a few different ways that we can solve first order differential equations. The first being separable variables. So if a first order ODE has separable variables, we can solve the ODE by quite simply taking all the x terms to one side, all the y terms to the other side of the equation, and integrating. If the equation is not separable but it is linear, then we can solve the linear first order ODE using the integrating factor method. If the equation is not separable, it's not linear, but it is exact, then in the last lecture, lecture 6, we covered how we can solve an exact equation. Okay? But if it turns out that the equation is not separable, not linear, and not exact, then we do have a few other tricks we can try to try and solve these differential equations. So today we're going to learn 3 substitutions that we can try in very specific cases to try and solve the ODE. And then secondly, the second new technique we'll look at is a different type of integrating factor. Okay. So let's get into it. So let's consider if we're given a differential equation that looks like it might be exact, okay, but it is not actually exact. So when we check the derivative, the partial derivative of m with respect to y, it is not equal to the partial derivative of n with respect to x. Okay, so it's not exact, it's not linear, it's not separable. Then it may be possible to transform the equation into one of these types using a substitution. Okay, so we're just going to take our variable y, which is our dependent variable, and we're going to transform that into some function of the independent variable x and some new substitution variable. Okay, so we're going to look at 3 cases here. U is a new substitution variable. The first case is homogeneous ODEs. Okay, and so this is very specific terminology. So if we have a function f of xy, if instead of looking at f of xy, if we multiply our variable x by t and our variable y by t, if we do that and evaluate the function, and that is equal to t to the power to some power alpha, where alpha is some real number, multiplied by the function f evaluated at xy. So if this is true, then the function is said to be a homogeneous equation, or a homogeneous function of degree alpha. Okay, now, so in terms of an ODE, a differential equation is said to be homogeneous if, when we have these functions m and n, if instead of evaluating them at the point xy, if we evaluate these two functions at the point t times x and the point t times y, so if we evaluate that function at those points, if we get t to the power of alpha times m at the point xy, t to the power of alpha times n at the point xy, where alpha has to be the same alpha for both of these equations, then alpha must be the same degree for m and n, so the same number, then we say that this differential equation is homogeneous. Okay, and if we show that this differential equation is homogeneous, then we can try one of the 2 substitutions: y equals u times x, where u is our new substitution variable, or we could try x is equal to v times y, okay, where v is a new substitution variable. Okay, so case 1, if we have an ODE that is not separable, not exact, and not linear, but it is homogeneous. So if we run this test, that we evaluate the functions m and n at tx and ty, and if it turns out that this function is homogeneous, then we're going to use one of these two substitutions. Okay. So we'll look at an example of this shortly, but I would just like to look at two other cases first. So case 1 was homogeneous equations. Case 2 is something called Bernoulli equations. Okay. So a very famous mathematician, Bernoulli. And what a Bernoulli equation is, this is an equation that almost looks linear, right? So if in fact n was to the power of 0 here, this would be a linear equation, like we saw earlier in this class. Okay, so the right hand side, so we have dy by dx multiplied by 1, so we're happy, plus some function of x only, the independent variable x, times y, so this is still linear, so we're happy. Now if we only had f of x on this right hand side, everything would be okay. This would be a linear equation, and we could solve this by using the integrating factor method. But because we've got this y to the power of n hanging around here, then this is not a linear equation, and we can't use the integrating factor method. However, what this is a Bernoulli equation, and so n is a real number not equal to 1. Okay, if it was equal to 1, what could we do? Well, if it was equal to 1, then we could combine this term on the right hand side with the p times y term on the left hand side, and in fact it would be linear. Okay, and we would just have a homogeneous equation because we'd have a 0 on the right hand side. Okay, so if it turns out we have a Bernoulli equation where n is not equal to 0 or n is not equal to 1, then we can use the substitution. This new variable u is equal to y to the power of 1 minus n. Okay, so the power of the y on the right hand side enters into the substitution variable. So we have y to the power of 1 minus n. Okay, and again we're gonna come back to an example of this shortly. But firstly, I just wanted to introduce you to case 3. So case 3 is equations of the form dy by dx equals some function of a times x plus b times, this should be a lowercase y, plus c. Okay, so some function of a times x plus b times y plus c, plus a constant c. A, b, and c are all constants. Then we can try the substitution. This new variable u is equal to a times x plus b times y plus c, where a, b, and c are just some constants, some real numbers. Okay, so summarizing the three cases here, if you have a homogeneous equation where you evaluate m and n at tx and ty, if we get that that is equal to m evaluated at xy times t to the power of alpha, and n evaluated at xy multiplied by t to the power of alpha, for the same alpha for both of these equations, then we're going to use the substitution y is equal to u times x. If we have a Bernoulli equation, dy by dx plus p of x, some function of x, times y, equals f of x, some function of x, times y to some power n, where n is not 0 or 1, then we're going to use this new variable, substitution variable u is equal to y to the power of 1 minus n. And then finally, if we have an equation that looks like so, dy by dx equals some function of a times x plus b times y, the variable y, plus c, then we're going to use the substitution variable u is equal to a times x plus b times y plus c, where a, b, and c are some constants. So let's look at some examples of that. Okay, so we've got this equation x times y plus y squared plus x squared all times dx minus x squared times dy equals 0. Okay, so straight away you can tell that this is not a linear equation, and it's also, you can try, but it's also not separable. So what should we do? Well, we should try and see if this is an exact equation, right? So m here is going to be the function of x and y that is multiplying dx, so this is m. N is going to be negative x squared, so just writing those down here. And remember, to test if this is exact, we're going to take the partial derivative of m with respect to y. So we're going to get x plus 2y. And we have to also check the partial derivative of n with respect to x, and that's going to be negative 2x. So x plus y negative 2x. These are not equal, okay? So m sub y, n sub x, where the subscripts are denoting taking a partial derivative, these are not equal. So the equation is not exact, okay? So unfortunately we can't use that method we learned in the previous lecture. But we could also check, if this equation is homogeneous, right? So if we evaluate m at the point tx and the point ty, everywhere we see an x here, we're going to replace it with a tx. Everywhere we see a y, we're going to replace it with a ty. So we get t of x times t of y plus t of y all squared plus t of x all squared. Okay, and if you pull out a factor of t squared there, you'll see that that is just simply x times y plus y squared plus x squared, which is equal to m, evaluated at the point xy. Similarly, for the function n, if I evaluate at tx and ty, I get negative tx squared, so I get something that is t squared times minus x squared, which is simply n evaluated at xy. So in fact, it turns out that this equation is homogeneous of order 2, because the power of t here is 2, the power of t here is 2, they're equal, therefore this equation is homogeneous. Okay. So what can we do? Well, we can say, well, let's try to use a substitution. We'll say y is equal to u multiplied by x, where u is just some function of x. Okay, so this is the ODE again. We're saying that y is equal to u of x. We can differentiate both sides of that equation to find dy. So again, this is appealing to second year calculus. We're calculating differential. So we're calculating the differential of y, which is equal to the partial derivative of y with respect to x times dx, plus the partial derivative of y with respect to u times du. Okay, well, the partial derivative of y with respect to x here, if I differentiate y equals ux with respect to x, then I'm just going to get u. So this is going to be dy equals u times dx, plus the partial derivative of y with respect to u is just going to be x. So we're going to get plus x times du. So dy equals u times dx plus x times du. And we can use this dy in our ODE. So any place we see dy, we can replace it with u times dx plus x times du. And any place we see y in the original differential equation, we can replace the y with u times x. Okay, so if I do that, I get x times, this used to be y, so now we're replacing it with x times u, plus, well, this used to be y squared, but now I've got ux all squared, plus x squared dx, it's all the same, minus x squared times, well, this used to be dy, but instead of dy now, I can write u times dx plus x times du equals 0. Okay. So now I might like to rearrange this equation because I have everything in this first term here is multiplied by dx, and I have another term over here on the right, the second term, which is also multiplied by dx. So I could combine those terms into a single term. Okay, I'm just pointing out what I've done there, but I explained it. I hope that's clear. So we can simplify this to u squared plus 1 times dx minus x times du equals 0. Okay. So what I've done here is I've taken this term minus x squared u dx and combine it with this first term, and then I've divided through by what would it be, by x squared. Okay, so perhaps you might like to try doing this little bit of algebra, and if you get stuck, feel free to post on the class stream page or send me an email. But the point is, now using this substitution, we have a new differential equation which is still nonlinear. It's still it's still nonlinear, but in fact it is quite nice though, because it is separable, right? So I can rearrange this equation into the form of a separable ODE. So I can take my du onto the right hand side by just adding x du. I can divide through by the x to get dx over x, so here I have dx over x. I can divide through by u squared plus 1 to get du over u squared plus 1. And then here I've also integrated. So now we've taken this nonlinear, non-exact, non-separable ODE that we had originally, and now it's a separable ODE, which of course is really straightforward to solve if you can evaluate these integrals. Okay, so if you recall, we solved an equation that was similar to this in one of the earlier classes. The integral of 1 over u squared plus 1 with respect to u is equal to arctan of u. The integral of 1 over x with respect to dx is log of x. And then of course we've got our integration constant c0 to take care of as well. So we can solve for u by taking the tangent of both sides of the equation, because if I take the tangent of the arctan of u, I just get left with u. So therefore the right hand side becomes the tangent of log of x plus some integration constant. And then finally I can rewrite this solution in terms of the original dependent variable y, because I can see from up here that y is just, let's say u is equal to y over x. So if I just rearrange this equation for u is equal to y over x. So y is going to be equal to x times tangent of log x plus c0. Okay. So because it turned out that this equation, although it wasn't exact, it wasn't linear, and it wasn't separable, because it turned out to be homogeneous, I could use this substitution to eventually find a ODE that was separable and solve the ODE. Okay, so let's take a look at another example. So again, this ODE is obviously not separable. You can try if you like, but it's not. It's not linear either, but it's almost linear, right? If I didn't have this y to the power of 3 thing here, it would actually be linear. But since I've learned about this thing called the Bernoulli equation, I know I can understand and I can see and I can classify this ODE, this first order ODE, as the Bernoulli equation. Okay, so it's a Bernoulli equation with n equals 3. Okay. So let's try the substitution. U is equal to y to the power of negative 2. So how did I get this? So if you recall that if my power was n there, I would use the substitution u is equal to y to the power of 1 minus n. So n is 3 here, 1 minus 3 is negative 2. So let's do this. So u is equal to y to the power of negative 2. I can rearrange that for y. So I can just take the square root of both sides, or let's say the negative square root of both sides. So then I would just get simply y is equal to u to the power of negative a half. Okay, so then I can differentiate this to find dy. So because y now is simply a function of one variable, but that one variable is a function of x, I can take the derivative of y with respect to x. So dy by dx is equal to, using the chain rule, dy by du equals dy by du multiplied by du by dx. Okay. So I can easily calculate this, right? So dy by du, I can differentiate this function here to simply get negative 1/2 u to the negative 3 halves. And du by dx, I'm just going to leave that as it is. Okay, I don't know the x dependence of u, so I can't do anything about this du by dx then. Okay, so now wherever I see a dy by dx in the equation, I can replace it with negative a half u to the power of negative 3 over 2 times du by dx. Okay, so this term here is going to be replaced, this term up here will be replaced by this term we've just derived. Anywhere I see a y, I can replace it with u to the power of negative 1 half. And then over here we have y to the power of 3. So if I take y to the power of 3 here, this is simply going to be u to the power of negative 3 halves, right? So I can simplify, well, or at least I can use these terms in the original ODE to write the ODE in terms of u rather than in terms of x. Okay, so dy by dx here, dy by dx we said was negative a half u to the negative 3 halves du by dx. So this is the term I've highlighted in red here. Y, 5 times y is equal to 5 times u to the negative 1 half. So that's what I have here, 5 times u to the negative 1 half. And then y cubed is just going to be u to the power of negative 3 halves. So I have this, still have this negative 5 over 2x, but now instead of y cubed, I have this u to the power of negative 3 halves. Okay, well, this is looking good. It looks a little bit more complicated at the moment, but I also note that I'd really like du by dx to be on its own here. Okay, so if I really want to get rid of this term that's multiplying du by dx. So to do that, I could multiply this, well, every term in this equation by negative 2. So the negative 2 will cancel the negative a half. We'll just get 1. Times u to the power of 3 halves, right? Because if I have u to the power of 3 halves times u to the power of negative 3 halves, that will give me u to the power of 0, which is 1. So I'll be left with du by dx. And if we look at what that does to the other terms in the equation, well, in fact, it makes the right-hand side a lot simpler too, right? Because u to the power of 3 halves times u to the power of negative 3 halves is going to give me u to the power of 0, which is equal to 1. So quite simply, if I do this, multiply all terms in the equation by negative 2u to the 3 halves, then I get this lovely linear equation, du by dx plus 10 times u equals 5x. So this is a linear first order equation, ODE, and we can solve this using an integrating factor. So to summarize what we've done here, we've taken a nonlinear ODE, which turned out to be a Bernoulli ODE. We've used the substitution u equals y to the power of negative 2. And using that substitution, we turn this equation into a first order linear equation in the dependent variable, in the new dependent variable u. Okay, so we know how to solve this kind of linear first order linear equation using an integrating factor. And so as your homework today and as practice for solving these types of equations, I'm going to leave this to you to solve, but just for your own sakes to check your solution against mine. This is the solution that I get when I solve this equation. C0 here is just an integration constant, and of course I'll solve this equation in terms of u, and then I substitute back into the variable y. Okay, so I end up with an equation in y, not with u at the end. So give that a go, please, and if you get something different to what I get, then please get in contact and we can talk about it. Okay, so moving on to the next example now. So we have this equation dy by dx equals y minus x minus 1 plus x minus y plus 2 all to the power of negative 1. Okay, so this is a first order equation. It's clearly non-linear, it's clearly not separable, and well, you might like to check it's not exact, but it's not exact either.
But we can see that this is somewhat similar in that we have some number times x plus some number times y plus a constant. And okay, so that's somewhat similar in both this first term here and this second term here, although the numbers in front of the x, y and the constant are not exactly the same. Okay, but we can actually rewrite this equation. So what I might do is I might subtract 1 from the negative 1 here, so I'll have y minus x minus 2, and to account for that 1 that I subtracted here, I should add a 1 at the end. Then I can multiply this bracketed term by negative 1, okay, because if I do that I'll get x minus y plus 2, which is exactly what I have in this second bracket here. So let's do that. So here if I subtract 1 from this bracketed term, add the 1 at the end to account for that, and multiply the first bracketed term by negative 1, then I get something that looks like negative of x minus y plus 2 plus x minus y plus 2 to the power of negative 1, and then plus this constant here. Okay, so the form that this is in now, this is some number a times x plus b times y plus c in both of these terms. So all the variables have this same structure, x minus y plus 2. So let's make that the substitution variable. U is equal to x minus y plus 2. Okay, well, let's differentiate this function u with respect to x now. Okay, and that's quite easy because, well, du by dx, if I differentiate the left-hand side, I'll get du by dx. If I differentiate the right-hand side, well, dx by dx is just 1. If I differentiate x with respect to x, I just get 1. To differentiate y with respect to x simply gives me dy by dx. And if I differentiate a constant with respect to x, of course I get 0, right? So I can differentiate both sides of this equation with respect to x, but we also have to remember that this dy by dx term here, I have an expression for that in terms of x minus y plus 2. Okay, so dy by dx equals x minus y plus 2 plus x minus y plus 2 all to the power of negative 1 plus 1. Remember though that I've made this substitution wherever I see x minus y plus 2, I can replace that with u. So I can write this dy by dx as dy by dx equals negative u, so negative u here, plus u, x minus y plus 2 is u, to the power of negative 1, or I can also rewrite that as 1 over u, plus 1. So dy by dx equals negative u plus 1 over u plus 1. And so I can, instead of writing dy by dx here, I can write negative u plus 1 over u plus 1. So if I substitute that into the equation, I end up with this very simple separable first order ODE. Du by dx equals u minus 1 over u. The 1's cancel here because I have a 1 minus dy by dx here. So I end up getting 1 minus the 1 over here. I get a separable first order ODE. So of course I can bring all the u terms to the left side. I can bring all the x terms to the right hand side, but I can also simplify this first actually. So u minus 1 over u, I can write that as u squared minus 1 over u. Okay, and that will make the algebra a little bit easier. Okay, so just to summarize what I've done in this example here, we started off with this differential equation. We rearranged it algebraically so that we got two terms that look like x minus y plus 2. I then made the substitution u equals x minus y plus 2, and using that substitution I was able to get an expression du by dx equals u squared minus 1 divided by u, so a separable ODE. Okay, and we know that separable ODEs are fairly easy to solve, so again I'm going to leave this one to you to solve, and the solution that I get when I separate the variables here and integrate is I get x minus y plus 2 all squared equals some integration constant a times the exponential of 2x plus 1 as an implicit solution to this ODE. I can't rearrange this equation to get y equals on its own, so I get some implicit solution. Okay, so we have three new ways of solving certain types of ODEs using a substitution. So we've got the three cases, case 1, case 2 and case 3. And so that gives us a little bit more ammunition to solve a wider variety of ODEs. But what happens if the ODE is not exact, is not linear, or is not separable, and these three substitutions that we've just learned, what happens if they don't work? So for example, the equation may not be homogeneous, it may not be a Bernoulli equation, and we may not have a nice substitution u equals a times x plus b times y plus c. We may not have that form or that structure in the solution. Okay, well there's one more method that we could try if everything else fails. Okay, so if we look at this ODE which has the form m of xy, so m is a function of the two variables, times dx plus n, which is also a function of the two variables, times dy equals 0, we can try and solve this using an integrating factor, but I should say a new integrating factor. Okay, the previous integrating factor we learned only worked for first order linear equations, whereas this method it potentially works for nonlinear equations as well. Okay, so what is the idea? The idea is that, well, let's say that we know that this is not an exact equation and nothing else has worked either. So we know that the derivative of m with respect to y is not equal to the derivative of n with respect to x. It could be possible that I could multiply this equation by a function that makes this an exact equation. Okay, and so the function I'm going to be multiplying by is this integrating factor. So we'll try to find an integrating factor which now depends on two variables, x and y. So our previous integrating factor only depended on the variable x. Okay, but now my new integrating factor is potentially a function of x and y. If I multiply that to the ODE, I get mu times m plus mu times n equals 0. Okay, and I'm saying if by multiplying by this mu, perhaps this new equation is exact. Okay, and of course this new equation is only exact if this new m, mu times m is our new m, if the partial derivative of this new m with respect to y, if that equals the partial derivative of this new n, mu times n, with respect to x. Okay, so this equation is exact if and only if mu times m differentiated with respect to y equals mu times n differentiated with respect to x. Okay, and so we've got, if we look at either side of the equation here, we have two functions, mu and m. Both are functions of x and y. So if I take the partial derivative with respect to y, then I'm going to have a product rule. Okay, so if I expand on the left and the right hand side here, the derivative on the left with respect to y, on the right with respect to x, using the product rule, then I get this thing. Okay, I get mu times the derivative of m with respect to y plus the derivative of mu with respect to y times m equals mu times nx plus mu x times n. Okay, the subscripts here again denote partial derivatives. Okay, well, this equation is still actually quite challenging to solve, so let's again make a simplifying assumption. Okay, I'm going to say that this equation that I'm trying to solve here, what if mu is a function of one variable only, so either x or y? Okay, well, we've seen an example of this in first order linear equations, but this equation doesn't necessarily have to be, the ODE that we started with doesn't necessarily have to be linear. Okay, so if we look at these cases individually, so if mu is a function of either x or either y, let's have a look at the case that mu is a function of x only. Okay, well if mu is a function of x only, then this partial derivative of mu with respect to x is actually equal to a normal derivative now, because mu is only a function of x. So mu sub x is equal to d mu by dx. But if mu is a function of x only, the partial derivative of mu with respect to y is equal to 0. Okay, so wherever I see a mu sub y over here, I can set that term equal to 0. And wherever I see a mu sub x over here, I can replace that mu sub x with d mu by dx. Okay, if I do that, I get this equation here. D mu by dx equals the partial derivative of m with respect to y minus the partial derivative of n with respect to x, all divided by n, multiplied by mu. So I'm just rearranging this equation up here, substituting in mu x equals d mu by dx and mu y equals 0. Okay, for this to be true, for both sides of these equations to be equal, I'm going to claim that this ratio, this fraction that we see here, m sub y minus n sub x over n, must be a function of x only. Okay, and that's true because I said here that mu is a function of x only. So this whole left-hand side of this equation is a function of x only. If the left-hand side of the equation is a function of x only, then surely the right-hand side of the equation should be a function of x only. Mu is a function of x, we already said in this case. So therefore this ratio here should also be a function of x only. Okay, so if it turns out that this ratio, m sub y minus n sub x, so these partial derivatives, divided by n, if that turns out to be a function of x only, then we can have an integrating factor that is mu, which is a function of x only. Okay. If that turns out to be the case, then this ODE that we have up here is a separable ODE. So I can rearrange, well, in fact, I can rearrange to put the mu, which is currently on the right-hand side. I can divide through by that, so I get d mu over mu. I can multiply through by dx, so I get m sub y minus n sub x over n times dx. If I integrate both sides, on the left I'm going to get a logarithm of mu, which I can then take the exponential of to find an expression for mu. Okay, so mu of x equals the exponential of the integral of this ratio times dx. Okay, and this is our integrating factor, which will make our original ODE exact when I multiply the original ODE by this mu here. Okay, but this is only true if this ratio, the partial derivative of m with respect to y minus the partial derivative of n with respect to x, all divided by n, is a function of x only. Okay. So let's take a look at the case where mu is a function of y only now. Okay, well, in that case, the partial derivative of mu with respect to x is equal to 0. The partial derivative of mu with respect to y can be written as d mu by dy equal as d mu by dy. We can follow the same steps as we did previously for when mu was a function of x only, and we find that the ratio, the fraction, the partial derivative of n with respect to x minus the partial derivative of m with respect to y divided by m must be a function of y only, and the integrating factor turns out to be the exponential of the integral of that ratio with respect to dy. Okay, so just to summarize here, if the ODE that we are given m times dx plus n times dy equals 0 is not solvable by any of the previous methods that we've previously tried, so including it is not an exact equation, then we can try an integrating factor, and it turns out that if the partial derivative of m with respect to y minus the partial derivative of n with respect to x divided by n is a function of x alone, then we'll try the integrating factor mu of x equals the exponential of the integral of this ratio with respect to dx. And similarly, if n sub x minus m sub y divided by m is a function of y alone, then we're going to try the integrating factor of this form here. Mu, which is a function of y, equals the exponential of the integral of n sub x minus m sub y over m with respect to dy. Okay, so if you take nothing away from this section of the lesson, this is the slide to print out. Okay, this is the slide to remember, to have available to you when you're trying to solve these problems. So let's look at an example now. So x times y times dx, so my function m is x times y, plus 2x squared plus 3y squared minus 20, so this is my function n times dy, equals 0. Okay, I can clearly see it's non-linear, I can clearly see it's not separable. I should check that it is exact or not, if it is exact or not. So again, m is just what's multiplying the dx, n is just what's multiplying the dy. If I take the partial derivative of m with respect to y, I just get x. If I take the partial derivative of n with respect to x, I get 4x. So these two things are not equal, and therefore the ODE is not exact. Okay, it's also not a Bernoulli equation, it's not our substitutions will also not work for this ODE. So let's try this integrating factor. Okay, well, if I'm careful, if I look at this ratio nx minus my over m, so these subscripts again denoting partial derivatives, I'm going to get 4x minus x over x times y. Okay, and of course this would make 3x over x times y. We get an x on the numerator and the denominator, which cancels out, and therefore we can simply say this fraction equals 3 over y is a function of y only. Okay, so that suggests that I can write an integrating factor mu as the exponential of the integral of this thing. Okay, well, this fraction n sub x minus m sub y over m equals 3 over y. So let's chuck that in our integral there. Okay, well, this is just going to be a logarithm, right? It's going to be the exponential of 3 times log of y. Okay, well, I can use the laws of exponentials here to write this as the exponential of the log of y cubed. The exponential and the log are inverse functions, and therefore I get that my integrating factor is equal to y cubed. Okay, so I've shown that this equation is not exact. I've shown that this ratio depends on y only, therefore I can define my integrating factor to be the exponential of the integral of that rational function times dy. And so I found that my integrating factor is simply y cubed. Okay, so got my original non-exact ODE, I've got my integrating factor here. I'm going to multiply this original ODE by the integrating factor. So x times y times dx times y cubed gives me x times y to the power of 4 dx. And then similarly I multiply every term in the n, the original n, by y cubed. And we get this here. And I'm going to claim that this is exact. You should check this, but it's not too hard to see, right? This m here, if I differentiate that with respect to y, I get 4 times x y cubed. This n here, if I differentiate that with respect to x, well, this is the only term with x in it, so I'm going to get 2 times 2 is 4 times x times y cubed. So now this equation is exact. We can solve it in exactly the same, using exactly the same method we did for any other exact equation. So I'm going to leave that again to you because this lecture is already getting quite long. But the point is really that we had an equation that wasn't exact, that wasn't solvable by any other means, but now using this integrating factor, I've turned this equation into an exact equation, which we can solve. Okay, great. So I'll see you in the next class where we will discuss graphical methods of learning information about ODEs that we perhaps can't solve using any of the methods that we've used so far. So I'll see you there.